Hello. Today you will be learning how to read potential energy diagram. And I'm asking you to bear with me. I'm learning this new tool that would allow me to draw on my slides, and probably I will be slow because of that. But still, let's try to see how it works out. So, potential energy diagram. It's a visual representation of the change of potential energy during the chemical process. So we would be able to see what's going on with the potential energy. Is it the amount of potential energy decreased um, throughout the chemical process, or is it increased? Is we would be able to predict whether this particular reaction is exothermic or endothermic just by looking at the potential energy diagram. So this one over here is the potential energy diagram for this reaction, which is, as we know, exothermic reaction of methane, the natural gas, burning in the oxygen, forming carbon dioxide and water. You see this reaction every day at the kitchen because this is what we use usually. The natural gas is methane burning with the oxygen. And we use this amount, this energy that is released in the process to boil the water, to prepare coffee and cook meals. Now, let's see how we read potential energy diagram. The y-axis over here shows us the amount of potential energy in different parts of the chemical reaction. And our x-axis represents reaction coordinate. Reaction coordinate means that it's a timeline of the reaction. We usually read this diagram from left to right. So my reactants are right here. It's a methane and oxygen. And their amount of potential energy represented right here. This letter A, this entire thing, represents the amount of potential energy stored inside of the methane and oxygen inside of my reactants. Okay, as the reaction proceeds and completes itself with formation of carbon dioxide, I have a bunch of products. Well, not bunch, I have specific products. Carbon dioxide and water has been formed, and I happen to know that the amount of potential energy stored inside of their chemical bonds is significantly lower. This is the amount of potential energy of my products. So this letter E over here represents amount of potential energy of products. And this one red over here, potential energy of reactants. Okay, and as you know now, the difference between the potential energy of the products and potential energy of the reactants is called heat of reaction. So this letter over here, the D, represents that heat of reaction. It is negative 890.4 kilojoules. How do I know that? Because in the reaction right here, I am given information about how much energy has been released alongside with carbon dioxide and water. And here is my products over here. Okay, so my letter D represents the heat of reaction. Nice. Now let's look at this interesting bump right here. Apparently, before my methane and oxygen turn themselves into carbon dioxide and water, they increase in the amount of potential energy. Well, there is happening so-called formation of activated complex. It's a temporarily, very short time period existing complex of methane and oxygen with the heightened amount of potential energy in it that we will call here activated complex. Only when methane and oxygen form this activated complex, only after that they can proceed to the formation of the products. So without some energy provided to reach this activated state, this entire reaction would not be even happening. Think about it this way. When you open the gas and let it go flow into the kitchen air, nothing is really burning right away. Methane and oxygen, there is plenty of oxygen in the air, are not starting to react with each other automatically. They are waiting for you to provide some kind of spark or bring the burning match, to actually give this extra energy to bring my methane and oxygen to the activated state, to the activated complex. To get them to form the activated complex, the energy needs to be provided for them. So this letter, this arrow B represents the activation energy. It's the amount of energy that needs to be provided to our reactants to let them climb the mountain and reach the state where they can form the activated complex. Once they are here, from here they can proceed to the formation of the products. Without this, without reaching the activated complex state, they will never even go and start reacting with each other. They will remain methane and oxygen, and nothing will change about them. And here, this long yellow line that I'm creating right now, let's give it a letter. Let's say that it's letter Z. Okay, this little Z represents potential energy of the activated complex that temporarily structure that exists for a very short period of time before it proceeds to completion of the reaction. Okay, to sum things up, the potential energy diagram is the visual representation of the changes in the amount of potential energy during the chemical reaction. So if we will consider this exothermic reaction happening, we will see that there is a certain amount of potential energy stored inside of the bonds of my reactants, and they are represented right here. This arrow with the letter A represents the potential energy of my reactants. Okay, as the reaction proceeds to the completion, the new products with the new amount of potential energy stored inside of their bonds is formed. And this line over here represents the amount of potential energy of my products. So this letter E arrow represents the amount of potential energy of my products. As our reactants absorb some energy to form an activated complex, they will gain certain amount of energy, the energy that needs to be given to them to activate them into the formation of activated complex and eventually proceed with the reaction. This amount of energy that is given to my reactants for them to be reaching activated complex is called activation energy. And this entire long line, which actually should be a little bit shorter because I overdid it, okay, is the amount of potential energy of the activated complex. This is the entire amount of potential energy inside of the activated complex. As soon as we are here, the reaction can go into the completion and formation of the products. A little bonus. You can tell that this reaction is exothermic just from the shape of the potential energy diagram. You can see that that the reactants have higher amount of energy than the products. As soon as we see this kind of shape, we know that the reaction was exothermic and the energy was released. This amount of energy was released into the surrounding of this in the form of heat. And the difference between the amount of and the difference between the amount of potential energy of products and reactants right here is the heat of the reaction that represents the amount of heat that has been released.